Hi, Kutch here. Today I'm going to be talking about using SR IOV for your NFV applications and the implications that may have on your decisions to use it. So we're going to be specifically talking about using SR IOV and OVS DPDK for traffic in two different traffic patterns. In general, when you have an NFV solution, your traffic has two different patterns. Either it's going to do what we call north-south traffic, where traffic comes into the platform, into your server, gets routed to a VNF, whether it's a VM or it's a container, and it gets processed within that VNF, and then it's sent back out to the physical wire again. So it comes in to the platform, gets processed, and sent right back out. The other way is east-west traffic. So this traffic is where the traffic, in this example, the traffic is going to come off of the wire, off of the switch, into the VNF, and then instead of going back out the platform, it's sent to another VM. And then it could be chained into more and more and more. So we call that service chaining. So that would be like if you're going to, you have your router and you have your firewall and your deep packet inspection, those kind of things you could run through a service chain all on the same platform. So the reason we're doing this is I started recently working in the area of NFV, and I did some research on that topic, and I found a number of articles online that talked about NFV and using SR IOV and PCIe pass-through to improve your performance, which makes sense because SR IOV is always going to give you your fastest performance and lowest latency because you don't have that software V-switch there in the middle. However, when I started digging into this and looking at the numbers, well, the numbers were impressive in a lot of these papers, some of them talking about offloads in their specific Ethernet device to be able to provide vSwitch type of offloads. They all talked about receive traffic, and only one or two VMs or VNFs in general were shown in the numbers. So they didn't talk about large scale, like 6 or 8 VMs, and they only talked about north-south traffic. They didn't talk about this east-west traffic flow that I discussed here, which is a valid use case. So that was never discussed. They only discussed the north-south flow. So what we decided to do, my partner in crime, Brian Johnson, and I put together this system here. And it's an Ubuntu box running KVM, and it has Open vSwitch, and it has OVS DPDK on it, which is DPDK extensions to Open vSwitch. And it's got some nice processors on it and lots of RAM, and it's got 9 virtual machines on it, all identical, and it has 3 independent Intel 40 gig Ethernet controllers on it. One of them goes straight into OVS. Another one goes into OVS DPDK, which means that there's a DPDK pull mode driver associated with it. If you want more information about DPDK, there's materials on the web that you can go find for that, and a link at the end of this presentation. And the last Ethernet controller is for SR IOV. So we made these all separate for the purpose of this test. And each VM looks like this. So we're going to have each VM is a Ubuntu virtual machine running on top of the system under test, and each of them have 3 different network interfaces. We have the SR IOV virtual function that's associated with the Intel 40 gig device. We have a DPDK backed paravirtualized interface that we call vhost for the purposes of this video and in the paper that this video is based upon. And that is OVS DPDK backed. So that means that there's a DPDK pull mode driver here that's reading data off of the Ethernet port and putting that into OVS, and then it goes up to this vhost device within the VM. And then lastly, we have the more traditional paravirtualized VirtIO driver that is backed within OVS by a vhost user device, and that is the traffic for that comes in off of the other NIC. Just using the standard I40E driver. So in this case, it's running with a regular interrupt. Traffic comes in, an interrupt is generated, and then it's processed and it's sent up to the VM here. So we're going to run 2 kinds of tests. The first test I will show you is running a traditional network stack what we call, in the VM over each of these three devices. So you can see what running NetPerf looks like on over SR IOV, DPDK, and over VirtIO. We are only going to show transmit numbers for this whole demo, just because it's almost identical with the receive side. But to me, it was more important to show the transmit because that's what the output of the VNF is. So we're going to show, first of all, a traditional network stack and see how these three different interfaces compare to each other in that kind of environment. And then we're also going to run tests for scaling using a more traditional VNF approach, which is where you're going to use a DPDK application to do that fast packet processing, because you're going to get your best performance on, especially in small packets, with using a DPDK. So for that, we're going to use test PMD, which comes with DPDK, and test PMD is simply going to read data as it comes in off of the interface. So in this case, let's do an example. We're going to run a test. We're going to use SR IOV. So test PMD is going to read data off the virtual function. It's going to use the pull mode driver, and it's going to read the data, and then it's going to write it right back out that device, that same device. So it's going to come in on SR IOV, and it's going to turn it and write it back right back out. All it's going to do is change the destination MAC address. So it's going to change it to the system, the remote link partner, or it's for north-south type traffic, or it's going to send it to the next VM. It's going to give it the MAC address of the next virtual machine if you're going to do a chain mode. So that's the basic test. And so we have the systems are going to look like this. On the left here, we have the system under test with the 9 VMs. So we have 8 VMs we're going to use for test PMD, and 1 VM we're going to do, we call that VM18 instead of the VNFs over here. We're going to do that NetPerf test on it, so you can see the traditional stack. These are all identical VMs. The only difference is that we're going to run NetPerf on this with a traditional stack, and on these we're going to run a DPDK application. And then we're getting data sent to these boxes over a 40 gig device from another system running Ubuntu and DPDK package in. So package in is going to be generating the traffic and sending it over to here. I want to talk quickly about optimizations. So both SR IOV and OVS DPDK have, and OVS itself, have lots of knobs and buttons you can twiddle to modify and improve performance under certain conditions. What we found, though, is that for the large number of VMs we're using, which is 9, if we did an enhancement to, say, the configuration for OVS DPDK, we found that a lot of times that would result in a degradation of performance for SR IOV, or vice versa. So we didn't do a whole lot of optimizations, except that we did CPU pinning for each one of the virtual machines that we're using, and in the DPDK pull mode drivers that is in OVS DPDK. So it's kind of like the baseline optimization. We didn't do a lot else. So what this means is the numbers you're going to see in this, we have lots of numbers and charts and gauges and dials and stuff. The numbers you're going to see in this are not optimal. So I can't stress that enough. This is not the best performance you're going to get. What we're going to do is we're going to show a side-by-side comparison of these three interfaces so you can make a judgment as to which one suits your NFV solution best, and the possible problems that each one of those interfaces could have under different situations. So now let's take a look at the traditional network stack on top of these three devices. Okay, so we're going to have NetPerf running on the remote system and NetPerf running on the virtual machine. The virtual machine is going to actually transmit the data. The NetPerf running the virtual machine is going to transmit data over one of these interfaces to the remote device, and we're going to capture the packets per second, or the gigabits per second being transmitted from each one of those interfaces. So let's start off with 128 bytes on the traditional VirtIO interface, and then we'll hit start here, and I'll go start running that test. And you can see we're around 9 gigs of data that's being transmitted. Okay, so now we're transmitting at 128 bytes and a number of threads. We're transmitting at 9 gigs at 128 byte packets. Now let's go to the DPDK backed DPDK OVS interface, and we'll run that, and it's about 7.8 gigs, so it's a little bit less. Now let's take a look at the same packet size, 128 bytes, and SR IOV. You'll see that it jumps up to almost 12 gigabits. So it's a much more performant interface. And as we increase the packet size, let's go back to VirtIO. Of course, with the packet size, the interface, it's easier to process. So the overhead from using OVS, because all this data has to be processed in OVS, right? So when you're using these other interfaces, you're not using SR IOV, then it all has to be touched by a CPU here for sorting. But SR IOV doesn't have to do that. But it's still pretty good. You're getting 20 gigs here on your OVS, on your VirtIO. So now if we go to the DPDK OVS DPDK, we're getting 13 gigs. So that's pretty decent. And SR IOV, we're transmitting at basically line rate at 512 bytes. We're doing 39 gigs. Again, these are not optimized interfaces. It's just a apples to apples kind of comparison. If you want to look at the whole chart here, we can look at, say, at 64 bytes. This is about what it's going to be. So you have your VirtIO, your OVS DPDK, and SR IOV. And if we bring them all up here, you can see what the data is. So you can see that OVS DPDK is pretty close in performance in this kind of situation to the VirtIO. Again, this is a traditional Ethernet stack, but SR IOV is always going to be more performant, especially at 512 bytes. SR IOV jumps up to pretty much line rate. But when you get up to large packet sizes, 64K, then they're all pretty much line rate. There's a little bit of a performance boost with SR IOV. So this is a traditional network stack here running on top of the VirtIO or the DPDK, OVS DPDK, and SR IOV. So now let's go take a look at when you're running a DPDK application in there. So now let's look at, first of all, let's look at the VirtIO, and we're going to do 64 bytes, and let's do 8 VMs. Okay, so let's run this. So 8 VMs will be there, and what's happening now is that the remote system is transmitting data to each one of the MAC addresses for the VirtIO interface, and you'll see the performance is so low that it doesn't even register within the precision of these gauges. It doesn't even register. So we're only doing 0.04 million packets spread over 8 VMs. It just doesn't register. However, if I jump over to the OVS DPDK interface and I do the same thing, you'll see that we're processing 5 gigs of data and 10.6 million packets per second. Now, the reason that the VirtIO interface does not work so well is because, this is what we're running right now. We're running test PMD on top of a VirtIO or a DPDK-backed device or SR IOV VF. So test PMD is a pull mode, so it's always pulling for data. Well, that's fine if you have a DPDK-backed device here because it's also pulling for data and they talk to each other. It's para-virtualized. Or for SR IOV, it owns that virtual function, so it can pull that data quite efficiently. However, when you're using this interface, the traditional interface into OVS here, this is a traditional driver, which is interrupt driven. So this is going to get data and fire an interrupt and put it into OVS for processing. But that interrupt, this doesn't work on it. Test PMD doesn't work on interrupt. It's a pull mode driver in there. So the fact that this is polling for data and this is interrupt driven, those two do not align very well. So if you're going to use a DPDK based application, then this is not a workable solution. The performance is just too bad to use. It's unusable. So let's go back to our demo here. So let's back this down to say 5 VMs here, and so at 8 VMs we're doing 5 gigs and 10.6 million packets. So let's back it down to 5 VMs and see what the difference is. Right? Not a whole bunch. It's 6 million packets and 6 gigs and 12.5 million packets. So that's pretty decent, right? Each one of these VMs is getting data and processing. Again, this is north-south, so the data is coming in, getting processed, and sent back out the wire. Now let's contrast that with SR IOV at 5 VMs. Again, this is 6 gigs, 12 million packets at 64 bytes. So we're going to run the same test over the SR IOV interface, and now you can see we're at 15 gigs, almost 16 gigs of throughput, and 32 million packets a second are being processed, almost 33. Again, it's north-south traffic only. And so this is the details of each one of the VMs. Each VM is processing the same amount, which is over about 6.6 million packets per second. And if we jump this up to 8 VMs, what you'll see is that these numbers are going to stay very consistent, almost identical. They're going to still be about 15 gigs and almost 32 million packets. That's because with SRV, the sorting is done in the hardware. It just grabs it and sorts it. So it's in Intel Ethernet, it's around robin queue. They're all treated equally unless you configure them otherwise. So in this case, each VM is processing almost 2 gigs of data and a little over 4 million packets per second. So SRV scales quite well for this north-south traffic pattern. The more VMs you add, it just equally divides up the available bandwidth and packet processing for that. With DPDK, OVS DPDK, it also scales, but it doesn't scale quite as well in our configuration. If we did some tweaks and modifications, we think it would, because the difference between like 2 VMs and 6 or 4 is it actually, the more VMs you add, the throughput kind of drops a little bit. And again, that's the way our configuration is, and you could optimize that so that wouldn't happen. But the end result is that still north-south traffic over SRIV is significantly faster, even into 1 VM. But if you change the packet size, so let's jump up to, let's stay with 8 VMs, and we'll do, say, 512 byte packets. Again, north-south traffic. As you would expect, the more packets per second, or the more gigabits we're pumping through, the larger the packet size, the fewer packets per second is processed, but the more gigabits. But for NFV, most people care about the small packet size, so we'll concentrate on those. But we'll leave this in a 512. You can see that we're doing 31 gigs here, which is pretty good. It's a 40 gig device, so we're pumping through 31 gigs here, and all these VMs are getting the data and processing it. We jump over to SR IOV again, still at 8 VMs, and you'll see that we're almost at line rate. We're at 38 gigs here. Okay. So now let's take a look at east-west traffic. So let's jump down to 4 VMs here, and we'll do east-west traffic. And we'll do it at 64 bytes again, because that's the favorite for NFV numbers. So here we can see this is the service chaining. So the traffic is coming in, it's getting processed by the VNF, and then it's being sent to the next VNF over the vSwitch. Again, it's OVS DPDK. I should note that all these numbers you're seeing here are on the transmit side. So this VM here is transmitting 2.53 gigs. That means it's been processed, and this is what it's transmitting, and it's transmitting 5.2528 million packets per second. And these number here is the aggregate. This is what the whole system is processing right now. So we're processing almost 10 gigs of data and 20 million packets. Just on the transmit. So if you really want to count it, you could double this. So it'd be 40 million packets if you wanted to count it that way on the RX and the TX. But we just do it this way. So each VM here now is getting a little over 2.5 gigs. And as we add more VMs here, let's jump up to 6. You can see that it pretty much stays the same. It's 2.5 gig or so through this chain. And we add more VMs, and it doesn't change much. It scales very nicely. In the east-west configuration, DPDK scales very, very nicely. So here we have 8 VMs at 64 bytes going through this chain. And this chain is, again, the traffic's coming in off the physical wire. It's getting routed to the first VNF through OVS DPDK, and then each subsequent VNF is writing the data back out using test PMD, and it's writing it to the next VNF in the chain until it gets to the last one, and it writes it. The destination MAC address is, again, our transmit system, our link partner over there. So in this situation, we have 8 VNFs that are running, and we're doing over 40 million packets per second. Okay, And if we change the packet size, you'll see that, for example, if we jump clear up to 15, 18 bytes, you'll see that the throughput here is we're doing 220 gigs of processing. Again, this is just transmit side, so some people like to double that number for the RX, but we're going to say 220 gigs is being processed by this system and 18 million packets. So now let's take a look at, let's go to SR IOV, and let's go down to 4 VMs like we did before. And with SR IOV, 64 bytes, each VNF is running only 2 gigs. So that's a bit less than we had with OVS DPDK. And each one is doing about 4 million packets. Okay, so we're doing around 8 gigs of throughput here total. And as we increase this, let's just jump right up to 8, make our point. You'll see that all the numbers are pretty much the same. They're all doing a little over 1.1 million, 1.1 gigs and 2.4 million packets per second. They're all the same, but it's not near as performant as the OVS DPDK. Let's jump back to that one. So this one is 9 gigs and 18 million packets, 19 million packets. Oops, let's go back to vhost. You can see that this was much more performant. And if we go to large packet sizes, remember that we were processing 200 gigs here, 220 gigs east-west at 15, 18 byte packets with OVS DPDK. Now if we do the same thing with SR IOV, you see that we're doing 44 gigs and 3 million, 3.6 million packets. So in an east-west situation, SR IOV is not near as performant as OVS DPDK. Now remember this number here, 44 million, because we're going to come back to that, okay? Now let's do a side-by-side comparison of these two things. So let's go back to 64 bytes, north-south traffic, and 8 VMs. So on the top here we have the SR IOV data, and on the bottom we're going to have the same thing over the OVS DPDK interface. So again, for north-south traffic, with 8 VMs here, we're pumping through 15 gigs and almost 32 million packets. But with OVS DPDK, recall, it was only 5 gigs and under 11 million packets. And as you increase the packet size, we'll jump up to 512 bytes. Remember, the throughput changes, the gigabits increases, but the number of packets per second goes down. Over here on the right is what each individual VNF is doing, what each individual VM. So if we go back to 64 bytes here, you can see that each VM is doing, with SRV, is doing about 2 gigs of throughput and transmitting 2 gigs and transmitting 4.02 million packets. However, OVS DPDK is about half a gig. Now let's look at this on a chart. So in the chart you can see on both situations there is a jump in performance from 1 VM to 2. That has to do with our configuration. Again, we could have twiddled some knobs to make 1 VM very performant, but again, we didn't do that. So let's just take 2 VMs here. What this shows is that at 2 VMs all the way to 8, that we're doing at 64 bytes, which is what this is, we're doing 15 gigs or so, all the way across. You add more VMs, doesn't matter. We're still processing 15 gigs, and we're still processing over 30 million packets per second. And as we add more VMs, there's a slight drop down here, and again, I think that has to do with our configuration. Now, as a contrast this with OVS DPDK, the same situation, you add more VMs, it doesn't get any better. It doesn't really scale. It actually drops. And I think that is, again, a configuration issue. But as you can see, the max performance just isn't there. It's 5 gigs and about a little over 10 million packets. So this is an example, again, of north-south traffic. And so for north-south type of traffic pattern, SR IOV is your most performant option, and that is because it doesn't touch the hypervisor, which could have some bad things. You don't have any of the vSwitch controls that you may need. But if you're just wanting raw traffic power, then north-south traffic SR IOV is going to be most performant because it doesn't touch that vSwitch at all. So it's just the pole mode driver is grabbing that data and it's going as fast as it can. Now let's contrast this with east-west traffic. We're still going to show these numbers with 64 byte packets because that's the one that most people will care about. And there's more data in the paper that this video is based upon, if you want to look at that. So here we're doing 64 bytes east-west traffic. So it's chaining through these VMs as shown in this little mini video here. And as you recall, with SR IOV, we were doing aggregate value of about 10 gigs. So all those 8 VMs together were processing 9 gigs and under 19 million packets per second. So if we go back to the individual VM here, you can see this is what each one of the individual VMs was doing. On OVS DPDK, we had a total throughput of 20 gigs and 40 million packets per second at 64 bytes, and each VM was processing more than twice of what the SR IOV VNF was doing. So the opposite seems to be true, especially at low packet sizes, is that north-south traffic, SR IOV was more than twice as performant as OVS DPDK, whereas in the east-west traffic, the opposite is true, is OVS DPDK is more performant. Again, these numbers can be improved, but not a lot, especially in the east-west traffic over SR IOV. You are going to run into a limitation, which is what we're getting at for the purpose of this paper. So this video. So let's take a look at our charts again. So here you can see at 64 bytes, we don't have a lot of gigabits here, right? It's pretty consistent though. It's about 9 gigs. No matter how many VMs you add, 2 to 8, you need at least 2 for a service chain, right? So it's going to be the same. And the packets per second also is very consistent. It's sticking around 18 million packets per second. No matter how many VNFs you add in the chain, it doesn't change the performance. It doesn't go up or down much. There's a little fluke here. That's probably in our test. So now, if you look at OVS DPDK, the gigabits here stays at around 20, right? We're doing about 20 gigs here, east-west traffic. But as you add more VNFs, there is more, the packets per second improves a lot. Actually, the gigabits goes up too. It's just this part of the chart, you don't see it. You will in a second. So as you add more VMs, it scales very nicely. The more VMs you add in this east-west traffic flow, the more packets you can process. Let's jump up to a higher packet size here so you can see it in a different view. So again, with the packets per second, the processed goes down because the larger the Ethernet packet size, the fewer that are processed per second, right? So now we have, let's just do the biggest one here. So we do 1518 bytes. And again, in SR IOV, we're doing 44 gigs all the way across. No matter if we have 2 VMs or we have 4 VMs or 8 VMs, it's still 44 gigs and 3.6 million packets. However, with OVS DPDK, we are doing each individual VM, right, is doing almost 28 gigs here and 2.3 million packets. So that's going to happen. Each one of those VMs in this chain is going to do that. So in aggregate, we're doing 220 gigs of processing and 18 million packets per second at a huge packet size. So let's talk about why SR IOV does not scale as well as OVS DPDK. The reason is that SR IOV is a PCIe technology. This means that when you transmit data from one VM to another over SR IOV, it has to go across the PCIe interface. So the Intel 40 gig devices that we're using are PCIe Gen 3 and they're by 8. So that means that the theoretical maximum speed that those could do over PCIe is actually 50 gigs. So we start off with a pool before we transmit any data. We start off with a 50 gigs that being available. So let's send 10 gigs through this chain here and take a look and see what happens. So now we're going to transmit 10 gigs and it gets routed through the hardware up to the VM test PMDs running there. It's going to read the data. So now we have used 10 gigs of our total 50 gigs. So we only have 40 gigs available on the receive side. PCIe has receive and transmit sides. So it's received 10 gigs. And now we're going to transmit it back out. So on one hop here, we have used 10 gigs out of our 50 gigs on both the transmit and receive. And every VM that this goes to chain through, it uses another 10 gigs. So by the time we get to 5 VNFs that have processed this data, we are out of bandwidth. We don't have any more bandwidth on this maximum potential PCIe interface. And in fact, almost no devices actually use that much, can actually support that much bandwidth. For example, the 40 gig devices that we are using for these tests for Intel, they have a 40 gig PHY on them, the physical interface. Internally, over the PCI interface, they can support around almost 45 gigs. But since the traffic comes, is restricted, it's a 40 gig link, you can't ever see that except on this kind of north or east-west kind of traffic. And in fact, if you recall from our video earlier, I said, hey, remember these numbers. When we were doing east-west traffic at the largest packet size, which was 15, 18 bytes and 8 VMs, we were doing, 5.5 gigs per VNF, which was a total of 44 gigs. So that kind of adds up nicely, doesn't it? Is that we're reaching the cap of that of the PCIe interface of that device. You can't go over it. You can divide it up over any number of VMs you want. If I drop this down to 4 VMs, it would still add up to be 44-ish gigs of data. And that limitation does not exist if you use OVS DPDK. This is because OVS DPDK is a software construct, right? Once that data is read by the pull mode driver and gets into the system, now the data moving from VM to VM is all done in software. It's done with, I don't know how the internals are, but it's like page swapping or mem copies, or they have all kinds of accelerated methods for this, but there is no PCIe overhead because that data is moved within the system itself. It doesn't actually have to go over the PCIe interface at all. So it scales very nicely for east-west traffic. Not so good for north-south traffic because SR IOV gives you that best interface and there's less overhead with the software. So what's our summary? The summary is there's this nice chart here that you can take a closer look at and get some more information. But basically, the point of this video and the paper that it was written upon is that there is no one solution fits all. SR IOV is not your end-all solution for everything. If you're doing a north-south type of traffic situation, it is ideal. If you need some vSwitch technology in there, then you can't use SR IOV, so you have to do something else. If you don't want to use DPDK, then using regular OVS is a good way to go. But if you want your VNF to use DPDK to have the most packets per second, then you really need to use OVS DPDK or some other DPDK pull mode driver to pump that data into your VNF. Each one of these technologies has their challenges and limitations. So the advice is you need to go and investigate the strengths and weaknesses of these. And you can have combinations of them on the same system, but there is no one solution that's best. There are trade-offs for all of them. So some of the learnings that I've had on this is that SRIV is the least latent. It's always your least latency because it doesn't have to go across any of those software layers. Your pull mode driver, if you're running DPDK in it, can just simply go pull that data and read as fast as it comes in. It also has less CPU utilization because it's only touched by the CPU in the VNF. It doesn't have to. There's no pull mode driver in the host that's pulling the data, and it's not being touched by OVS. So it is a little bit more efficient in that way. However, as you probably know, if you know anything about SRIV, that it is hardware dependent. So your VNFs have to know about the devices it can talk to. So that makes live migration a challenge. It has been since SRIV came out. It is a challenge. There are methods to do it, but they're not easy. It's a pretty heavy lift. Observations and learnings about DPDK. DPDK is super powerful and it performs and scales with the CPU and software enhancements. So during the process, the 6 months that it took us to go to do all these experiments and set everything up in our spare time and write this GUI and everything, we upgraded processors and we upgraded the version of DPDK, and it gave us a pretty significant performance boost. So what this means is that DPDK will become even more performant with every generation of processor. So right now, with the system we had, it's between 5 and 7 million packets per second is pretty much the maximum that OVS DPDK can read data off of a physical port and process it. And as those CPUs get more performant and the software gets more and more refined, that number will do nothing but go up. So it's going to continue to be a really good solution. And I don't think it'll ever be as performant as SR IOV, again, because it's still being touched by software layers. DPDK has a steep learning curve. It's not easy to use. You have to noodle on it quite a bit, and it's not like other Intel Ethernet technologies where the logo is it just works. And there's lots of knobs. I mean, there's lots of things you can modify, pinning to cores and setting buffer sizes, and there's lots and lots of things you can do to set all that stuff up. And as with SR IOV, it does have its challenges in live migration. Again, because you have to have a OVS DPDK device in your VM, and if you migrate that to another system, then there has to be something there for the to hook up to and communicate with. Some resources. So the paper that we wrote that has all this information and all the data that was collected, the hundreds of different data points that are used to make the charts and graphs in the document are all documented in there, as is our test setup and our findings and why PCIe bandwidth is your limiting factor for your SR IOV solution. There's DPDK, you can go learn about that. The instrumentation framework that I wrote, the GUI based on is up on GitHub. I happen to write it, so you can go up there and grab it and start making your own GUIs if you like. And then if you want more information about SR IOV and other stuff that I've written about and did videos about, you can go look at the YouTube channel here listed. So in summary, I'd like to say SR IOV, again, is great for north-south traffic, but when you start doing east-west, it just doesn't scale. And it doesn't matter if it's a smart NIC or it has all these offloads on it. The fact is it has to go over that PCIe interface to go, if your traffic is routed over PCIe to provide your solution for east-west traffic, you're going to run into the same problem. Doesn't matter if you upgrade to a 100 gig NIC, you're still not going to be able to push 100 gig through all those VNFs in that mechanism. So you may want a hybrid thing where you use SR IOV to get data into a VNF at 100 gig, and then you use OVS DPDK to do the service chaining, and then the last VNF will send it back out SR IOV, for example. Bottom line, look at your options, do some experiments, and realize that there is a menu of options that is available to you, and you need to pick and choose and develop your solution in that mechanism. I hope this has been helpful. Thank you.